Okay, hello friends. So we'll try to see how to plot the FFT of any signal in MATLAB. So let us consider the basic signal as sine wave, the AM sine 2 pi ft. If you see my last video, I already told how to plot this sine wave. So let us go ahead now. So as just a brief, AM is a peak amplitude of the signal, 2 is a constant, pi is a constant, f is a frequency of the signal, t is a time axis. So we need to decide how many points of a sine wave we want to take. We cannot take infinite number of points. So t will decide how many points we want to take. So let us consider the sampling frequency as 10240. Let us consider the sampling frequency as 10240. So the signal length we are taking as 256, and we will let us take the FFT length as same as signal length, or I can say 256 points itself. So when we are considering the FFT, okay, so let us first see how to plot the sine wave. We have taken the frequency of sine wave as 120 hertz. The time axis is divided from 0 to 1 by fs to 255 by fs. Signal length is 256, so it is 255 by fs. Total, the t will be the matrix of size 1 by 256. So this will be plotting the sine wave. So this is, for details of this part, we can refer my previous video of plotting the basic signals or plotting the sine wave in MATLAB. So let us consider the FFT part. There is an inbuilt function in the MATLAB which uses the FFT function or FFT. So we can provide the FFT, the signal sine, whatever the signal that we have generated, and the FFT length. If you do not provide the FFT length to this, it will be taking the default length as the signal length, or the multiple of the 2 raised to the 2's power, you can say, like 8, 2 raised to 2, 2 raised to 3, 2 raised to 4, like that. It will be so here the FFT length is 256, signal length is also 256, so we are getting the 256 point FFT of the signal. Now if the generally the FFT will be the complex FFT, so we cannot plot the complex values directly. Either we have to plot the magnitude or you have to plot the phase of that. So let us plot the magnitude, or you can say the absolute value of that. That will be this, just simply the absolute value of this FFT of the signal. Now let us see, uh, if you refer the Parseval's theorem on the somewhere on the internet, the energy in the time domain should be same as energy in the frequency domain. However, if you take the FFT of the signal, uh, simply the 50 of the sine wave, which is having the peak amplitude of 1 volts, should be having the two peaks at minus fm and plus fm of amplitude of zero point 0.5 each. So total amplitude becomes 1. So that is the law of conservation of energy simply. But here when you are taking the FFT, you will be getting the peak amplitude of 128. But that is what not desired. So we divide this FFT magnitude, the amplitude value is divided by the total FFT length. So 128 divided by 256 will be getting 0.5, just to satisfy the law of conservation of energy or the Parseval's theorem. Now when you are plotting the FFT though, this FFT is simply the 256 values. So we have to plot these values on appropriate x-axis. The x-axis is a frequency axis. So we must provide the frequency ranges from which the lower frequency range and the higher frequency range from which these points will be ranging from. Now there is something called the FFT resolution or the frequency resolution. This is the formula for the frequency resolution. You must remember this. Fs is a sampling frequency. We are dividing the entire sampling frequency range into these many points, or you can say 256 points. So one point will be representing the lowest frequency, you can say. If you can step in, you can see we have the Fs of 10240. The FFT length is 256. So entire sampling, which is 10240, which ranges from some minus Fs to plus Fs, or you can say minus Fs by 2 to plus Fs by 2. Each point is having the frequency value of 40 hertz. Okay, so each point is having the frequency value of 40 hertz. If you are getting the peak in the first point, you mean your frequency ranges from 0 to 40 hertz. If you are getting the peak in a third point, your frequency ranges from 40 into 3, 120 hertz. Okay, so this is called as frequency resolution. Resolution means the lowest frequency that your FFT can identify. So simply, if you are taking the more number of FFT points or FFT length, you will be getting the better resolution. You can identify the lowest frequency even than 40 hertz. So we are taking the frequency of the signal as 120 hertz. So simply your resolution is 40, your frequency is 20, means one point will represent the 40 hertz. You have frequency of 120, means it will be the peak will be the third point, or you can say the third bin will be representing your peak. Okay, so now let us see how to provide the x-axis values or frequency axis values. Okay, sorry. Okay, so this is the line space. Line space is an inbuilt function of MATLAB that divides the axis in equal number of parts. So we have the fs as a frequency. So we will divide the x-axis or the frequency axis from ranging from negative frequencies minus fs by 2 to plus fs by 2. Total it is 10240. Okay, so these many points in total to 56 number of points. Again repeat, we take entire frequency axis, we divide it from minus fs by 2 to plus fs by 2, and total number of points are 256 points. Just remember, 0 is also included in the frequency. Therefore, we need to take just 1 point less, one frequency value less, because otherwise that will be 257. So it is from minus fs by 2 to plus fs by 2 minus one value less, because 0 is already included in the positive frequencies. So including zeros, it will be one frequency less. So this is the frequency axis values. Now simply you have to just stem. I can say you simply say the plot also, but the spectrum will be discrete. Therefore, we need to say stem. This is the frequency axis, and we have to plot the 50 sine magnitude. As you know, we have taken the sine magnitude, we have divided by the FFT length, and then just we have to understand what is this FFT shift. Okay, so what MATLAB does is MATLAB simply uh, takes the okay. So FFT computation, if you try to understand, is simply like this. We are getting the 256.50 means 256 bins or 256 frequency sets or frequency values we are getting. In that, if you are getting the peak in this bin and your resolution is 40, means 40 into 3, it will be 120 hertz. Simply, it is a 50 of sine wave. As you know, we should get two peaks. The nature of FFT calculation is like when we are taking just a bins, it is simply this is if you're considering the zero frequency here, this side contains the negative frequencies. Remember, this side contains the negative frequencies, and this side contains the positive frequencies. This side contains the positive frequencies, but practically we want negative frequencies on left side and positive frequencies on right side. So what FFT shift does is just picks up this entire thing and puts it here before this, so that negative frequencies are on left side, positive frequencies are on right side. Just FFT shifts just simply does the arrangement, that is inbuilt function of MATLAB, which rearranges the spectrum, because practical calculations gives negative frequencies here and positive frequencies here. We want negative frequencies on left side and positive frequencies on right side. Simply that shifts this axis or this part of FFT to the left side. So let us see FFT shift. that is here. Then just say title X level as frequency, Y level as signal amplitude, grid on. Okay, so you can see simply here. This is a sine wave that we already plotted. This is the 50 of sine wave. We are done it as stem. As you can see, this is a zero frequency. Frequency that we have already chosen, our first sine wave was 120 hertz. So we're getting the peaks at minus 120 and plus 120. And your amplitude, if you are checking, it is 0.5 on each side. So total amplitude becomes 1, so that the law of conservation of energy is satisfied. This is simply the FFT of sine wave. Remember one thing here, if you are taking the FFT, the main thing is if you want to get this exact peaks, this F should be integral multiple of this FFT resolution. Here FFT resolution is 40, so I have taken the integral multiple of 40, that is multiple of 40 into 3, that is 120. If there is not integral multiple, say for example if it is 50, or let us take 130, you should see a spectral leakage. The FFT is your pin number cannot be a non-integer, but FFT understands just that your frequency is 130, means it is somewhere lying between 120 and one, I can say 160. So between these two bins, the energy is spreaded, because it just understands that there is no in between bin, because your resolution is 40 hertz. It can understand the multiples of 40. So it says there is a spectral value which is somewhere in between these two. So it is 130 is nearer to 120. Therefore, this peak will be higher as compared to the peak at 160 hertz. This is called as spectral leakage. So if you want to just for a demonstration purpose, if you want, you can keep the frequency of the signal as integral multiple of this frequency resolution. So this is simply the sine FFT of the sine wave. Here we have taken the absolute value of FFT. If you want the angle of this, or you can say the imaginary part of this, if you want to take the angle, or you can say the imaginary part of this sine wave FFT, you can just simply write IMAG here. So we'll be getting something like this. So the negative frequencies, we are getting the positive angles, or and for positive frequencies, we are getting the negative amplitude. So this is the imaginary part of the FFT of the sine wave. So similarly, you can plot it for the cos. You can simply change here as cos. Now this is the cos. We have taken the imaginary part of cos. Cos is in real signal. It is not having any imaginary part. Therefore, you can see the amplitude is very less. It is simply the noise. You can see simply noise. So it is very less. This is nothing but 0. So we have plotted it as the imaginary part. If you plot the real part or absolute value, you can see the 50 of cos wave also. So it is again same thing, 120 hertz minus n plus 120 hertz with amplitude of 0.5. So you can try with other signals as well. Just the main thing is you have to remember, if you want to get exact peaks, your f should be integral multiple of this FFT resolution, multiple of 1, 2, 3, and so on. If you give some other value, then you will see the spectral leakage. You may not be able to find an exact peak. Thank you.